Hello, everyone, and welcome to our Unit 2 extra practice problems in order to get ready to help get more practice getting ready for Exam 2. Now, as a reminder about these things, this is not an exhaustive list, and just because these things show up here, it doesn't mean that they'll show up on the exam. Um, but I feel like a lot of these questions are going to be very good at going over main themes of the different sections of Unit 2. It would be my recommendation that you should pause the video and try and do all these problems yourself first before looking into the solutions to them. So without further ado, though, let's go ahead and get started. Question one says a parabola has a vertex at 3 comma negative 3 comma 7 and crosses the point negative 1 comma 9. Find the x-intercepts of f. So in order to find the x-intercepts of f, I need to know what the equation of f is. And right now, all I'm given is the vertex, but that's a good thing. That gives me the h and k value of a vertex because as a reminder, vertex form is y equals, or f of x equals, a times x minus h squared plus k. That's vertex form. So if I know what h and I know what k are, I have almost everything I need to create the equation of f. So let's actually just change this to f. Then I can use the given point to plug that into the equation to find the corresponding a value, as you'll see in just a moment. So from the vertex, I now know that f of x is equal to a times x plus 3, because remember, plus 3 squared, because remember it's x minus h, so minus negative 3 is plus, and then plus 7. Now, this point right here tells me that f of negative 1 is equal to negative 9. So we can use that to our advantage. So f of x is equal to, or sorry, f of negative 1 is equal to a, and if I plug in negative 1 for x, I get negative 1 plus 3 squared plus 7 is equal to negative 9. And I can solve for a now, because this is going to be 2, and it's squared, so it's 4, so it's 4a plus 7 is equal to negative 9. I'll subtract 7 from both sides, divide by 4, and I will get that a is equal to negative 4. Because if I subtract 7, I get negative 16, and divide that by 4, I get negative 4. So now I know the equation of f. F of x is now therefore negative 4 times x plus 3 squared plus 7, and I need to find the x-intercepts. And as a reminder about x-intercepts, those are the places where you cross the x-axis, which happens precisely when y equals 0, and y is synonymous with your function values, f of x. So for an x-intercept, I'm setting y equal to 0, which is the same thing as saying set f of x equal to 0, because these two things are synonymous. So that is, I've got negative 4 times x plus 3 squared plus 7 is equal to 0. Also, I could FOIL this out, do the x squared plus 6x plus 9, and then distribute the negative 4, and then simplify and use the quadratic formula. Or I can utilize the fact that this has the square root property already set up for us, which is the thing that says if you have box squared equals a number, then box is equal to this plus or minus the square root of that number. So in this case, I'll subtract 7 and divide by negative 4 and get that x plus 3 quantity squared is equal to 7 fourths, because the negatives cancel each other out. It'll be negative 7 divided by negative 4, the negatives cancel out. And I'll take the square root of both sides. Don't forget about the plus or minus. And the whole point of that is that cancels the square root in the square. And I get x is equal to, x plus 3, rather, is equal to plus or minus the square root of 7 fourths, which you could rewrite as plus or minus the square root of 7 over 2, because that's the square root of 7 over the square root of 4. Square root of 4 is 2. Square root of 7 is in a nice square, so that leaves it as is. So the x-intercepts are x equals negative 3 plus or minus the square root of 7 divided by 2. And that is our answer. And the question didn't ask it to be rounded or to write it as an exact form or to write it as a coordinate point. So I can just leave it like this. Next, we'll move on to question two, which says consider this polynomial, which has been given in factored form, and we need to sketch it. So as a reminder, when it comes to sketching a graph of a polynomial, we need to know its zeros and their multiplicities, and we also need to know its end behavior. And we also need to know its y-intercept. We're not going to worry about y scaling. So for this one, end behavior, which I'm going to abbreviate EB, should be like y equals 1/2 x to the seventh. And for the reason for that is if you were to FOIL all this out, remember, end behavior only comes from the leading term. So if I were to distribute this, and this would be x to the fourth plus a bunch of stuff, this would be x squared plus a bunch of stuff, and this is x minus 6. When I combine all of this without the 1/2, it'll be x to the sixth plus a bunch of lower degree terms, and then I'll multiply that by x minus 6, and that'll give me x to the seventh plus a bunch of lower degree terms, which don't matter for end behavior. Last but not least, I'll multiply by the 1/2, and that's why it has end behavior like this. And if you remember what that graph looks like, this graph will look roughly like this because it's an odd power of x, which means it makes the squiggle shape. And because the leading coefficient is positive, it'll fall on the left and rise on the right. So let's go ahead and write our end behavior. Our function f falls left and rises right. You can also use the calculus notation, but this is the way our textbook does it. So that's the way we're going to continue with it. And also because we're not taking calculus right now. Then we also have to find the zeros and their multiplicities. So the zeros, and my recommendation is to always write them in ascending order. So from most negative to most positive. Our zeros, just to write them out for a second, are 0, -4, 2, and 6. Those are our zeros or our roots, as I usually like to say. So writing them in ascending order, that would be -4, 0, 2, and 6. And their corresponding multiplicities is the number of times the factor occurs. -4's factor occurs only once, so it has a multiplicity of 1. 0 has a multiplicity of 3. 2 has a multiplicity of 2. And 6 has a multiplicity of 1. Now that we have that, we have everything we technically need, though one thing, what actually not technically everything we need. We also want to know its y-intercept. Now we already have that technically speaking because it has an x-intercept at 0. It has a root at 0, which is also known as an x-intercept. And if it has a root at 0, then that means that you have the point 0, 0, which is the only point that is both an x and y-intercept. But let's just make sure we are generalizable to any problem. So f of 0, because remember, for a y-intercept, you're setting x equal to 0, but with a function notation, that means plugging in 0. And that would just end up being 0 times a bunch of 0 minus 4 plus 4 times dot dot dot. It just equals 0. Like, because this thing is 0, it all goes away. So we know what our y-intercept is, we know our zeros, we know our end behavior, so we're going to draw a graph. I'm going to pause it real quick. Boom. And so let's go ahead and we're going to assume that each tick mark represents 1. And let's go ahead and let's draw our end behavior. So it's down on the left and up on the right. That'll tell us how to start and where we should finish. And then let's plot all of our zeros. So -4, oh, what is that? -4, 0, 2, and 6. And then we should also plot our y-intercept, but we already did. Normally it's going to be something up here or here. It's probably going to be an obscene number, so we're just going to say this is 1,000 or 100 or whatever. But either way. So now we're going to start working through it. So we start down here and we have to move up to our 0 at -4. That has a multiplicity of 1, so we should cross through. And we get to decide how much we go up. It's your choice, but then eventually it has to come down. Now, 0 has a multiplicity of 3, which means that it'll also cross through, but it'll be more wiggly. So it's probably going to look like that. But once again, as I've said in class, as long as you make sure you go through, that is enough for me. If you want it to look prettier, you'll do the whole squiggle line, like more accurate, you'll do the squiggly line, but it's not required. Then we go to 2, which has a multiplicity of 2, so it should bounce there. So maybe it goes down and then it goes and bounces back down. And maybe it goes further, maybe it goes less. It's hard to know unless you have calculus under your belt, which we don't have. So I'm going to make it go down lower, but it could be not the case. The curve could look like this, but we don't know. So we'll just use our channel our inner Bob Ross and then go back up. And this 0 at 6 has a multiplicity of 1, so it should cross through in a nice line-shaped pattern. And we ended where we should end, so we know we did it correctly. Onwards to question 3, which says to factor p of x completely. Now, it didn't give in this one, unlike previous ones where we're given some zeros that we know about it, like sometimes it'll say provide like factor it completely provided the information that p of 1 is equal to 0 or p of negative 1 is equal to 0 or something like that. So, we're going to have to use the rational zeros theorem. We need to use the rational zeros theorem. So that means we got to remember about Pooh Sam. So x is equal to p sub 0 over q sub n. Let me technically plus or minus. So p sub 0 are factors of a sub 0, and q sub n are factors of a sub n. And so the factors of 18 are 1, 2, 3, 6, 9, and 18. And the factors of 2 are 1 and 2. So we've got quite a few. We get plus or minus 1. I'm just going to write the plus or minus once and like make sure that goes throughout. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18, and then plus or minus 1 half, plus or minus 2 halves, but that's 1 and we already have that, plus or minus 3 halves, plus or minus 6 halves, which is 3 and we have already got that, plus or minus 9 halves, and plus or minus 18 halves, which is 9, and we've already got that, so we don't need to write it down. Now the goal is to go through and plug them in using our calculator to see if we get 0. So that's what we're going to do. First, I'll try P of 1, and that equals 24. I've already plugged it into my calculator, so, but on an exam, you'd want to make sure you put it in parentheses so that you can go through and edit it and just change the entry, the 1 to a negative 1 to a 2, and then a negative 2, and then a 3, and then a negative 3, and so on and so forth. Next, we'll find P of negative 1, and I'm going to pause the recording just to do it quickly. And we get 0, which means that that is, in fact, a factor. So we'll go ahead and start synthetically dividing so that we can factor it out. So we got to make sure we got negative 1, and then all powers of x are present here. So we don't need to put any placeholders, and we'll move on from there, bring down the first term, and then multiply diagonally, add vertically. Negative 1 times 2 is negative 2. Let's add them together. That's negative 9. Negative 1 times negative 9 is positive 10. Negative 11 plus 10 is negative 1. 1 times negative 1 is 38. Or like it's one to no, negative 1 times negative 1 is 1. That's 38. And negative 1 times 38 is negative. No. What am I doing? What am I doing? Okay. I was getting ahead of myself and just thinking about adding. Okay, negative 1 times negative 9 is positive 9. Negative 9 plus negative 11 plus 9 is negative 2. Negative 1 times negative 2 is positive 2. That gives me 39. Then I get negative 39 and add them together. I get negative 18. And then I get positive 18, which gives me 0. So P of x can now be factored into x minus negative 1. So that's x plus 1 times 2x squared, or 2x to the fourth minus 9x cubed minus 2x squared plus 39x minus 18. And let's just call this new smaller polynomial, we'll call that q of x. And and now we're going to do the same thing. Now, good news is the leading coefficient and the constant term are the exact same as before, so these guys are still the same. So I don't need to rewrite them anything like that. And I've already checked p of 1. I've already checked to see if x minus 1 was a factor, and it wasn't. So I'm just going to switch on to q of negative 1, which is negative 48. I did need to check negative 1 again because it could be a repeated root. It could have a multiplicity of 2. Then we'll move on to 2's. And q of 2 should equal 12, so that's not a 0. Then we'll try q of negative 2, which is equal to 0 if you plug it into your calculator, which means that x plus 2 is a factor of q and thusly a factor of p. So we'll go ahead and utilize that to synthetically divide on q. So negative 2 synthetically divided into 2x to the fourth minus 9x cubed minus 2x squared plus 39x minus 18. All powers of x are present and accounted for. That's why I say it out loud. Though on an exam, you probably just want to say it in your head. Bring down the 2, get negative 4, brings me negative 13, gives me positive 26, which gives me 24, which gives me negative 48, which gives me negative 9, which gives me positive 18, which gives me 0. So, with this in mind, now p of x is equal to x plus 1, then x minus negative 2, so x plus 2, times 2x cubed minus 13x squared plus 24x minus 9. Each time, the reason why it's now the cube power is because I divided by a degree 1 polynomial. That the quotient that you get when you divide would be 1 less because we divided by a degree 1. It was originally a degree 4, and now it's going to be degree 3. Now, we've got a reduced list because now the constant term is 9 instead of 18. So our new list of options, I'm just going to write them in green, are plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 1 half, plus or minus 3 halves, and plus or minus 9 halves. Now, we don't need to check 1 or negative 1. And the reason why we needed to check negative 1 with q because we weren't sure whether or not it was a repeated root. But once we saw that negative 1 didn't work, we were confident that we don't need to check it anymore. So we can actually just cross those out and we'll just look at let's call this uh, m of x. And so we'll do m of 3, which is equal to, luckily enough, it's 0. So just as a reminder, the reason why I didn't bother plugging in 1 or negative 1, I don't need to check in 1 because it's not a factor of p, which means it can't be a factor of m. I don't need to plug in negative 1 because when I tried to plug it into q, it wasn't a factor of q. And this right here, this is q. So it can't be a factor. If it's not a factor of this, it can't be a factor of this. And so I went to 3, and that ended up being 0. So we'll do one more synthetic division. We got 3 divided into m of x, which is 2x cubed minus 13x squared plus 24x minus 9. All powers of x are present and accounted for. Bring down the 2. 2 times 3 is 6. That gives me negative 7, right? Yeah, negative 7. That gives me positive negative 21, which gives me positive 3, which gives me 9, which gives me 0. And so p of x is equal to x plus 1 times x plus 2 times x minus 3 times 2x squared minus 7x plus 3. Now I could sit down and work through this one and do more. I could do the rational zeros theorem again, but this thing probably factors nicely, and it does actually. This becomes x plus 1, x plus 2, x minus 3, and then this thing will factor to 2x, x, minus 3 and plus 1, right? Because that'll give me plus x minus, oh, minus 1, minus 1, 2x minus 1. Because that'll give me negative x minus 6x, which gives me that negative 7x. And there we have it. That is the factored form of p of x. So that'll do it for this one. And so now we'll move on to the next one, which is about 2.5 material. So it's given the rational function r of x is equal to x cubed minus 2x squared minus 15x over x squared minus 4. Find the x-intercepts, y-intercepts, and any asymptotes, and then graph the function. So first and foremost, what I always like to do with these ones is I like to write it in its unfactored form, because this helps me find out this is really nice for plugging in values, and it's also really nice for finding any horizontal asymptotes. And then I'll write it in its factored form, which was going to be x times x minus 5 times x plus 3 over x plus 2 times x minus 2. Now notice that nothing cancels, so this rational function will have zero holes. It won't have any removable discontinuities. So for x-intercepts, we're setting the function equal to 0 to set the y value equal to 0, but that can only happen if the numerator equals 0, so that gives me x equals 0, 5, and negative 3. I set the numerator equal to 0, that's where I get 0, positive 5, and negative 3. For y-intercepts, or y-intercept rather, I find r of 0 if it exists, and if I do that, I'm going to plug it in here because, I mean, actually for this one, it's quite quick if you do it with this version of it. But regardless, it gives me 0 minus 0 minus 0 over 0 minus 4. That's 0 over negative 4, which is 0. Which we already knew because we had an x-intercept at 0. But just to be generalizable, that's what we've got. Now, we had no holes, but we do have vertical asymptotes where the new denominator equals 0. The new denominator and the old denominator end up being the same thing because nothing canceled, but regardless, that gives us x equals negative 2 and positive 2. So, last thing is to look for HAs, of which there are none. And the reason for that is we look at the degrees. The highest degree term, the degree of the numerator is 3, the degree of the denominator is 2. So the degree of the numerator is larger, which means that at infinities, at the positive and negative infinities, this blows up much, much faster. So it does not have a horizontal asymptote. However, the numerator is exactly one more than the degree of the denominator. So we have an OA, an oblique asymptote. And we do that by dividing. Now, this time, unlike the one we saw in class, this denominator is not of the form x minus c. So we can't do synthetic, we have to do long division. So x cubed minus 2x squared minus 15x plus 0, because we need to have a constant term placeholder. And then we ask ourselves, how many times does x squared go into x cubed? It goes into it x times. Then we get x cubed minus 4x. And we subtract that, right? Because x times x squared is x cubed. X times negative 4 is negative 4x. And then we'll bring down the negative 2x squared because nothing got subtracted from it. And then it's going to be minus 11x and then plus 0. We don't even really need to write it, but either way. And then we ask ourselves, how many times does x x squared go into negative 2x squared? And it goes into it negative 2 times. And we get a negative 2x squared plus 8. And we subtract this. And these cancel. That's by design. And we get negative 11x because nothing can subtract from that. And then a minus 8. And our quotient becomes our oblique asymptote. So we have an oblique asymptote at y equals x minus 2. That is going to be the line for our oblique asymptote. Now, with that all taken care of, we have everything we need to graph it. Well, not everything. Um, so, we can plot a few points, and that's the way we have initially learned it. But what I would prefer to do is to make a sign chart to figure it out. So, if I look back at x times x minus 5 times x plus 3 over x plus 2 times x minus 2. The VIPs would be x equals 0, 5, -3, -2, and +2. So we'll make a sign chart. I know that's a lot of numbers, but it's going to be fine. So we'll draw. So the most negative is -3. Let's make that space. -2, 0, 2. I guess we're going to need to make this go a little bit longer, and that's okay. And then 5. And we'll pick some test values in between. X equals -4, x equals -2.5, x equals -1, x equals 1, x equals 3, and x equals 6. And then we just need to plug it in and look for the signs. If we plug in -4, we get negative, negative, negative up top, and a negative times a negative. That's 5 overall negatives. That's an odd number of negatives, which results in a net negative. So we're below the x-axis here. Plugging in -2.5, we're going to get negative, negative, positive over a negative times a negative. That's four negatives, which is a net positive. And in between -3 and 2, we're going to be above the x-axis. Then at -1, we're going to get negative, negative, positive over a positive times a negative. That's 3 negatives, so that's negative, and it goes below here. Then between, we'll plug in 1, we get a positive times a negative times a positive over a positive times a negative. That's 2 net negatives, or 2 negatives, which is a net positive, and we'll be above the x-axis there. Plugging in 3, we'll get a positive times a negative times a positive over a positive times a positive, which is a net negative. So it's below the x-axis here. And then last but not least, we get a positive times a positive times a positive over a positive times a positive. And it's positive and it's above the x-axis here. So I'm going to create a little graph. Boom, and then we will start filling in all the details. First and foremost, let's graph our vertical asymptotes, which we're at -2 and 2. Come on, there we go. -2 and +2. And then we had our vertical asymptote, or our oblique asymptote at y equals x minus 2. That has a y-intercept of -2 and a slope of 1. So I can either plot, so I go up 1 over 1 to plot the point -1 comma -1, or I can go up 2 over 2. It really doesn't matter, just to make sure like my graph is already kind of scrunched in for space. So I'm going to go ahead and do that and then draw a line connecting those 2 points. And I'll move it down. That's pretty good. Next, I'm going to start plotting all my points. So I had x-intercepts at 0, at 5, and at -3 right there. And so we have to hug our asymptotes. We know that between -infinity and -3, we're below the x-axis. And since we have to hug it, we're probably going to come up to it like that. And then between -2 and 3, so right in this little tiny segment right here, we're above the x-axis. So we're going to have to hug our asymptote like that. Then, so let's go ahead and create that portion. Next, between -2 and 0, we're below the x-axis. So we're going to have to come up from here and go to it. And then between 0 and positive 2, we're positive, so we've got to come back up like that. And then, as you might imagine, from 2 to 5, so in this little segment, we're below the x-axis, so we have to start down here because we have to hug our asymptote. And then after 5, we're above the x-axis, so we're going to be up like that. And that completes our graph. So you can use this. Now, this was a very, very technically, like, this is a very hard example, but it's designed that way. Um, Normally, we only get like 3 or 4 of them instead of 5. And usually we only have like 1 or 2 asymptotes, and usually it's a horizontal asymptote. I digress. So usually we don't have this many spots to work with. And the other option is to, of course, remember to just plot different points to figure out the shape. Like plot f of -5, f of -2.5, f of -1, f of +1, and then f of 3 and f of 6 or something like that to get the rough shape of the graph. But I prefer using my sign charts because it's more practice with sign charts and it does it faster. And on to the last problem. Solve the inequality 2 over x plus 5 is less than or equal to 3 over 2x minus 1. Now, just like before, just like with anything, we want to bring everything to one side. So we get 2 over x plus 5, leave a little bit of space, and then write the minus 3 over 2x minus 1 is less than or equal to 0. And actually leave a little bit of space after that, too. Because these things aren't multiplied together at all, we need to find a common denominator. So I'm going to multiply the first one by 2x minus 1 over 2x minus 1, and I'll multiply the second one by x plus 5 over x plus 5 to cleverly multiply by 1. Doing so will give me 4x minus 2 minus 3x minus 15, all divided by x plus 5 times 2x minus 1 is less than or equal to 0. By multiplying by what I did in red and blue, I ensure that they have the exact same denominator, so I can combine them right off the bat. 2 distributed into here gives me the 4x minus 2, and then -3 distributed into the x and the 5 gives me a minus 3x and a minus 15. Simplifying it, I get x minus 17 over x plus 5 times 2x minus 1 is less than or equal to 0. So my VIPs are going to be x equals 17, -5, and 1/2. And I'm going to highlight these last two, because those are problematic VIPs, because they make the denominator equal to 0. And if they make the denominator equal to 0, it results in undefined, which is not less than or greater than or equal to 0. So they don't solve the inequality. So we need to make sure we keep them in mind when we're trying to write our solution set. So looking at this, let's plot -5, positive 1/2, and 17. And we'll pick some test values. X equals -6, X equals 0, X equals 1, and X equals 18. But you can use whatever numbers you want inside each interval. If we plug in -6, we'll get a negative up top and then a negative times a negative, which is a net negative. And that is going to be a piece that I want because I want to be less than or equal to 0. Before I forget, let's highlight the -5 and the positive 1/2. To remind myself, I cannot include those. Back to the problem at hand. That is a piece that I want. Then I plug in 0, I'll get negative up top, and then a positive times a negative down bottom. That is a net positive. That is not a piece I want. I want to be strictly less I want to be less than or equal to 0. Plugging in 1, I will get a negative over a positive times a positive. That is a negative, and that is a piece that I want. And last but not least, if I plug in 18, I'll get a positive over a positive times a positive, which is a net positive and not a piece that I want. Yes, this one did go from negative to positive to negative to positive. Um, but that is not always guaranteed. Sometimes it goes negative, negative, positive, positive, negative, positive, positive, negative. It all depends. So you have to test the values. So, knowing that I cannot, this is a non-strict inequality, meaning that I need to worry about including things, brackets. I need to keep in mind that I cannot include negative 5, nor can I include 1/2. So the answer is negative infinity to negative 5, but I can't include it, so I use a parenthesis. Union this interval from 1/2, but I can't include 1/2, all the way up to 17, but I can include 17 because that does in fact solve this inequality. If I plug in 17, I get 0 is less than or equal to 0, which is a true statement. And that is my answer, and that will complete our little extra practice pre-lecture. I hope it helps you in your studying, but also make sure you look over the exam review and your notes and any of your homework assignments, and then feel free to use Alex to also do some practice. And I'll see you guys in the next one.